Hello, everyone. Welcome back to Foresight's Intelligent Cooperation Group. Today, we're lucky to have Abhishek. He's a fifth-year Ph.D. student from MIT Media Lab. His research interests are collective intelligence, self-organization, and decentralized machine learning. And the central question to his research is, how can we engineer adaptive networks to build anti-fragile systems? And he's also a 2024 Foresight Fellow. So with that being said, Abhishek, please take it away.
For the introduction. And it's very interesting to see we are entering this era where we have half humans and half bots agents attending the Zoom meeting. So I'm very excited to present to my AI overlords as well. And actually, this talk is related to that topic as well in some ways, where I'm going to be talking about this orchestration between agents, humans, and agents as well. So yeah, title of my talk is Decentralized AI for Personalized Health. And the way to flesh out the agenda, I'm first going to focus on like motivation, like why do we even need decentralized AI in the first place? Because you might have heard of decentralized AI before, but there are different perspectives on why do we need it. And then I'm going to be talking about 3 dimensions of decentralized AI: coordination, heterogeneity, scalability. And this is going to be more of an introduction for the first 20 minutes. And then remaining half, I'm going to focus on one very specific narrow technique that I've been developing in my PhD, and then trying to bring all these things together. Okay, let's start with a very broad overview. So a decade ago, I believe, at this point of time, Yuval Harari has this talk on why humans run the world. And the question is very intriguing because we have lots of species, and obviously the question is, what is it about humans that make us so special and help us be one of this top species? And he talks about these 2 different models. So one is this model known as Hive approach, which is you have amazing scalability. So you have lots of agents, which are in this case birds in this flock example, but you have low heterogeneity. So all of them are behaving in a very similar way. The other model you have is this pack of wolves in this example, where you have low scalability. Typically, the pack of wolves will be limited to a size of around 10. Sometimes it goes all the way to 30, but usually does not exceed that. But at the same time, we have very high heterogeneity, and by heterogeneity here we mean different roles and capabilities are assumed by different members in the pack. And his argument is what makes us special is this notion of heterogeneity and scalability at the same time. And in order to do that, we have to invent these, what I'm going to call as local protocols or frameworks. You could think of many creation myths, even things like money, judicial system. These are protocols that are enabling these heterogeneous, diverse groups of people sitting in today's world everywhere on geographically distributed, and at the same time still be able to collaborate. Now, if we view this problem more of as a scalability and heterogeneity as 2 goals, and the goal is to enable coordination while keeping scalability and heterogeneity, we run into this trilemma of centralized systems, where if a single system is trying to take care of scalability and heterogeneity, then coordination is not as much, this is where you end up in this disorganized state, which I have drawn on the left. Or if you go in a heavily heterogeneous but coordinated setting, you end up in this constrained system, which is in some ways trying to say that it's not scalable. And that was the example of this pack of wolves, where each agent is heterogeneous, assume different roles and capabilities, but at the same time, the system does not scale to a large population. And then finally, the notion of homogeneous system is where this example of flock and hives come in, where you have large scale systems, but at the same time, roles and responsibilities are pretty similar and heterogeneity is not much there. And the argument is actually not just true for this, let's say, species, abstraction layer of species, but it's also applicable at other layers as well. If you think about how design of economy works, you have this free market system versus something which is much more socialist, where you are culling heterogeneity to a certain degree to enable scaling, and then you have a small scale system where you allow high heterogeneity. So this is where decentralized systems become very important, because when you have local protocols through which coordination can be mediated. So one simple example would be something like money, where as long as different agents in the system believe in its utility, then they can act independently and pursue their own objectives heterogeneously. But at the same time, they will be able to coordinate at a large scale just because they believe in this concept of money. But that's true for many other things. And hence, going back to Harari's argument, what he says that the capability which makes us really be able to achieve coordination while scalable and being heterogeneous is this notion of storytelling, language, and all these things, where we tell these stories so that we can coordinate with each other at a large scale. So that's the decentralization pitch for you all. But now you might be wondering, what has it got to do with AI? So let's focus on healthcare now, because that's one of the most consequential, also one of the most promised applications for AI. So let's look at this landscape of how things have been evolving in AI so far. So these LLMs, chatbots you might have been using, like ChatGPT or Claude, they are mostly trained on publicly accessible data. In some cases, they have used data which was not publicly accessible, and that's why they're also getting sued for that. We will ignore that aspect. But other than that, we can say they're, for the most part, trained on this publicly available data sets like Wikipedia, Reddit posts, and Twitter posts, and so on. And there are a lot more interesting things which are not publicly accessible on the web, but are still very important and useful for the things we want to achieve with AI. And one of them, which I'm primarily interested in, is healthcare, and specifically all these siloed healthcare data sets, which we just cannot share and put it on the web, right? Because we care about privacy, and there are some regulations which prevent sharing of this kind of data. So as the slide says on the left, you can't solve what you can't see. So these LLMs are generally AI models, unless they have been trained extensively on a lot of different healthcare data sets spread across different hospitals, logged in silos such as patient databases and so on, is just not accessible to train. So imagine if we could actually build an AI model that was trained on these data sets. And one thing we know is that there's plenty of data available when it comes to healthcare. And we know because two things are increasing at the same time. So quantity, as in how quickly we sample these, let's say, biological or medical information. So you have this variable market, which is like really growing very fast, collecting lots of different kinds of data thanks to all the advances in sensing, but also genome sequencing and all this whole multi-omics revolution, which is going on right now. And then we have biomedical imaging and so on. So we have lots of different modalities of data. And we have also increase in how quickly we sample them. So that's on the increase in data sets argument. We are also seeing increase in intelligence. So this is the scaling law paper, which showed that as you add more compute or more data sets, you are actually enhancing intelligence as measured by test loss in this case, which is debate in AI community whether it's a good representation of intelligence or not, but let's assume it is. We are really seeing increased intelligence as more and more resources are getting added. So two things, right? Data sets are increasing, intelligence in this context is increasing, and yet we are not able to merge these two worlds very, let's say, tightly enough. So this is where the setting which my research operates in comes in. So imagine you have this network of data owners. It could be hospitals, it could be patients, or it could be something in between as well. Imagine you have these patients and you want to enable collaboration across them so that all these data sets, whether they get shared or not, actually, like revealing their sensitive information or not, is, let's say, somewhat abstracted here. But imagine if we could build machine learning models or generally AI capabilities that perform as good as if they had access to all these data sets at a single place. So we are not saying that, hey, we are actually going to combine these data sets at a single place to build AI, but we are saying the data will remain distributed, decentralized, but we are going to change some of these AI algorithms so that this notion of building intelligence without centralizing data set becomes feasible. So when it comes to building this collaboration network, we have been thinking about how this progression has been happening in the industry so far. And you can generally think there are three levels, and there is this level 0 also, which I'll be talking about. But broadly, there are three levels and three ways to approach this problem. And every time you step up a level, you enable new capabilities which were not possible before. So level 0 is just a strawman argument where you have a single hospital which is just using its own data set, its own experts within those, let's say, silos in order to just build basically whatever analysis they can do. And then in level 1, which is what a lot of research like in bioinformatics right now people are doing, is they're leveraging these crowdsourced or public data sets available, or they do their own study and then they're relying on that. And at level 1 systems, we are able to do, let's say, basic research, but it's not, first of all, hyper personalized to a point where it can help guide individual journeys, but also it's usually not able to account for the whole picture, because data sets that are open source or publicly available usually will not have any sensitive information, which is sometimes required to build these good capabilities for healthcare. And then in level 2, you might have heard of this thing called federated learning, for instance, where the idea is we can train multiple models jointly across multiple institutions. And instead of sharing data, we can combine these models together so that we can enable this more decentralized data intelligence, where data is sitting in their own silos, but we still have model that can perform really good. The only issue with this level 2, although it's a very good progression from level 1, is that it prevents participation from many, let's say, independent stakeholders in the system. So it's the way usually it's coordinated, because federated learning depends upon central coordination. There has to be a central coordinator. It requires multiple participating entities to first have their own contracts and come together to build this kind of a consortium, and then be able to train these machine learning models. And then finally, level 3, which is where a lot of my current research is focused on. And before, I also worked on several areas in level 2 collaboration as well. And level 3 becomes interesting because now it's patient centric. What it means is it's able to get to the resolution level of individuals, and it is permissionless. So you do not need to have all these contracts and consortiums. And the goal is to enable participation across multiple agents to join the system and be able to build models, use them with their own incentives. And the system does not have a single central controlling entity to guide individual behavior. And the place where in our lab we see the advantage of these approaches is, one is rare diseases, because that's a place where individually there's not enough data at any single institution, but then collectively there's plenty of data. It's just that it's fragmented and distributed at a large scale. And also longitudinal. So longitudinal data sets typically are missing in a lot of our healthcare research. And one of the reasons is follow-ups are difficult. People are switching their hospitals, so the data is getting more and more fragmented. And generally, if you want to build these models, then you need to be able to access information about these patients or biological specimens across multiple centers, essentially. So the goal is to go all the way to level 3. But then there are some challenges, and which is what my talk will be focusing on, how to address some of those challenges. But I'll give like a quick overview. So as we talked when I was giving this trilemma figure before, that there are three challenges: coordination, heterogeneity, and scalability. So the goal is to enable coordination among these large number of agents that are behaving in their own ways. And that's why the system is heterogeneous also. So an institution might have compute capacity, for example. Another institution might have lots of data. And if we can combine and enable collaboration between these two institutions while respecting their own incentives and constraints like privacy, trade secrets, and so on, then we can enable coordination between such heterogeneous agents. And the goal is not to enable this collaboration between just a few large institutions, because then it would be possible with these contracts and consortium approach. But the goal is to go all the way at the patient-centric level. And that's why scalability becomes very important. Another reason scalability becomes very important in this context is we want to show that these decentralized approaches actually can outperform some of their centralized counterparts, and that only happens at a large scale. So the goal essentially is to then summarize and solve these three challenges: coordination, heterogeneity, scalability. And now what I'm quickly gonna do is go through these challenges and describe what are different levels of coordination, heterogeneity, and scalability. So let's start with coordination. So level 0, again, more like a strawman argument that you have no communication. Think of these siloed healthcare data sets within single institutions. Then you have level 1, coordination. So this is static. Then you have level 2, dynamic, and then finally adaptive. And I'm gonna quickly mention what these things mean. So as I said, no communication. So you have these islands of data which are not talking to each other. And we need to figure out how do we even connect them in the first place so that they start leveraging data sets that are at other places to improve decision making and modeling at other places. So let's start with simple static coordination example. So one way to connect these systems is by saying, okay, this is the default way they are going to be connected. And this can work for some system. Just like in this example, you have a ring like static coordination so that agents can interact with each other and learn from each other essentially. And this is another example of like wiring up these different agents or data holders in these cases. And again, if you have heard of federated learning before, then think of federated learning as a special case of static coordination, and the topology would be something known as spoke and hub, basically. So now let's go to more interesting levels. So dynamic coordination. So here we have seen some interesting algorithms. Many of them are based on what is known as randomized collaboration. So instead of by rule defining agent A is going to talk to agent B, now here we are in this regime where different agents can be connected in a randomized manner. And the benefit of this kind of collaboration is it's more fault tolerant, because if a few agents die in the system, it's not going to completely disconnect, because after some random rewiring across multiple collaboration rounds, different agents will be talking to each other. And random is just a special example of dynamic category, but there are some other categories also. Like another is you cluster them based on similarity. So in this case, I'm just taking one specific example of clustering, but you can imagine other ways of clustering. So here, a specific group of patients are talking to each other based on the task they are interested in. And you could, something I did not give as part of the premise in the talk is you usually have well-defined tasks. For example, one task could be given these genomic data sets. We want to, let's say, build a polygenic risk scoring model. Going beyond this level 2 coordination, let's quickly jump to adaptive coordination. So this is where these ideas get very interesting and, let's say, more relevant for real world deployments. So the idea is you want to learn instead of just defining these dynamic topologies or static topology, like how we learn how the neural network is wired, and that's how these machine learning models are trained today. We also want to learn which agent should talk to whom, because at a very large scale, every agent has different information, and identifying whose information is relevant to whom becomes very important, because if you do something like random collaboration or static collaboration, then you're not accounting for similarity in data points and also how they collaborate. So that's adaptive coordination. And then I'm quickly gonna talk about heterogeneity levels. So level 0 is just everyone has similar resources, and the objective they're going for is globally defined. Level 1 is also similar, except the nodes can have different resources. And then level 2, we have more interesting and practical, let's say, approach, which is that everyone has this personal objective. So my goal depends upon my lifestyle, my genomics data sets, and so on. And hence the model has to be accounting for those factors. And then finally, level 3 becomes even more real world and practical, where we say that agents can have actually competing resources and complementary assets. So how do we enable coordination at that scale? So now going a slightly deep into weeds, you can imagine you're doing distributed training of neural networks. And today, when large big tech companies are training their AI model, this is the technique they use, which is in this case, it's a different compute node, which is training same model on a different partition of data set, but these data sets and model partitions are shared across different compute nodes in the data center, something also known as data parallel training. There are some other names for it if you're interested in these areas, like pipeline parallelism, model parallelism, and so on. But the idea is same. The objective is global and the resources are shared across agents. Then we have this interesting level one, which is you have different data sets across different agents and they cannot be shared at a global scale. So the objective is still the same, which is to build one single global model, but the resources are somewhat different or similar as I'm saying it here, but they're not exactly the same. That's the key distinction from level 0. And federated learning, split learning from our lab, and these kind of examples fit in this category. Level 2 gets interesting. So imagine you have different agents with different modalities of data. Agent A has their, in this case, let's say, DNA methylation data set. And then agent B has some blood test result. Agent C has biomedical imaging. And then agent D has this histology data set. And we still want to be able to create this capability to enable collaboration across these agents. What that means is identifying what are the patterns that are similar across different modalities of data without having to combine these data sets at a single place. And this problem has been relatively addressed in certain cases. So there's something called multitask learning in federated learning, or notions of meta learning and so on. And here the idea is, how do we make sure, even though resources are heterogeneous, the agents are still able to collaborate. Finally, okay, so this is also different example, but instead of changing too much in the data like previous, now we are changing the models themselves. So imagine I have my MacBook, someone has their smartphone, and someone has a whole data center with them with different compute capacities. Can we still collaborate? That's the question there. And quickly jumping to level 3, we have different institutions as well as individuals with their own modalities of data sets, but also some institutions have, let's say, only compute capacity or models. Some institutions have money to contribute. Now, how do we enable collaboration in think of a diverse mix or a zoo of agents with their own incentives and their own goals, but they should still be able to participate. And some problems which make this whole setup very challenging is things like privacy and malicious attackers. So that completes heterogeneity. And now let's come to scalability. So here in scalability, we have this constraint level, which is the system is really difficult to scale beyond a point. And then what we see, and this is, I would argue, more or less the state of the art in some of these techniques today, is this notion of parallelization, that multiple agents can train their models, do inference in parallel. But then things also start getting interesting and more practical once you have these asynchronous systems. So these parallel systems still have to synchronize once in a while to be able to coordinate with each other. And something we have been exploring in our lab is how to make these systems more asynchronous so that they can train and participate at different point in time and still be able to benefit from each other. And then finally, this category, which I'm calling is self-scaling, the idea where different agents can scale in a self-organized manner rather than a centralized fashion. So let's quickly jump into them one by one. So constraint, as I said, if you think of something like a ring topology between multiple agents with their own data sets, and now if you have to introduce a new agent in this, think of this topology, then the amount of time taken to do all the computation and synchronization increases linearly in this case as you add more agents, which is usually not a good idea. From a computation complexity point of view, you want sublinear algorithms. Parallelizable becomes very interesting from that point of view because it allows different agents to do their own thing in parallel, then synchronize once in a while. and still be able to leverage each other's resources, be able to collaborate and coordinate. So things again like model parallelism, pipeline parallelism become important here. So in asynchronous system, as I was telling before, the idea is imagine you have these two agents. One of them is offline at a given moment, but the other agent can make their contribution. And then in the next phase, the first agent who was online goes offline now, and the second agent becomes online and becomes available. And now the question is, how do we enable collaboration at this point? And this is something which traditional techniques like federated learning and other variants are not able to solve because they fundamentally require this notion of synchronization once in a while. So we and a few others also at different locations, in different labs have proposed their own way. And roughly, I would say the approach boils down to doing some kind of a synthetic data sharing instead of sharing models. And finally, we have this notion of self-scaling. So imagine, in this case, I'm giving example of robustness, that you have some faulty nodes that are part of the system. Then you have to reorganize, or as I like to usually call it, self-organize the system so that faulty nodes do not influence the system too much and the overall system rewires itself to make sure it's stable over time and does not get corrupted by malicious attackers and so on. So that concludes the three, let's say, main pillars. And now I'm going to talk about more of solutions. So far, I've been talking about, okay, these are challenges and that's how things are in the current landscape, but a recent solution which we have proposed. So a very broad overview of how we're thinking about decentralizing all these three aspects I talked about is by making information private. What that means is you can share wisdom and not raw data. And then that way you can still enable collaboration between these different data owners, but at the same time prevent leakage of information. And once you give privacy to people, it's important to make sure that the claims they make or the models they contribute are verifiable. Otherwise, we run into the problem of bad actors. And then incentives is also important to encourage participation. That's more or less self-explanatory. So I'm going to jump to orchestration, something I'm most excited about, where if you have lots of these agents, imagine like billions of agents, right? Then how do we enable who should talk to whom, how should they collaborate, and so on? And we have been building a lot of interesting research algorithms and systems to make sure this orchestration is possible at a large scale. And finally, crowd UX, which is more about, so all these four previous pillars are focused on technical solution. But if technical solutions are not accessible, then only a few people are going to use them. So it's very important to make sure that the user experience for general public is very straightforward so that they can participate in this permissionless and all decentralized system and everything. Okay, finally, we are gonna talk about this technique, CodeDream. So before I jump into the technique, let's quickly see what it is getting built upon. So I think in 2015, a paper came out, or a blog came out called DeepDream from Google, where they showed they can represent what kind of knowledge a model has learned by just optimizing a random image on the model weights to, let's say, maximize some output. And generally what ends up happening is through this optimization procedure, you end up finding, so in the start you have a random image, but by the end you have this very hallucination kind of image, which is showing lots of features that a model has learned to recognize an image. So in this case, you see a lot of features that roughly look like something close to a dog. And the way this image was obtained by saying, hey, here's a random image, optimize it so that a pre-trained model thinks it's a dog. So that idea was used for a lot of AI art, as people like to call it, generate these hallucinatory images. But we decided to use this same approach, but now use it for exchanging knowledge across multiple models. Because if you can reveal what knowledge this model has, then other agents with their own models can use this information. So this approach we call as CodeDream. So what on the right is a similar version of what I was showing on this slide with dog image, but this time this is more useful for training a new machine learning model. So they still look a little bit hallucinatory, and you can feel there are some features, but you cannot really identify any single object or something discernible to a human eye. And the reason is it's capturing what machine learning models visualize in an image. And then what we do in our CodeDream approach is just doing this dreaming collaboratively, is by exchanging these dreams across multiple agents and using that as knowledge base to enable training across multiple agents. So let's see in more detail. So here the idea is, and I suppose figure might be confusing, so try to follow the numbers. So there is a first stage of knowledge extraction where you start with a random input. Each agent has their own local model. You can think of something like a biomedical image, and they're optimizing this input on their local models. Then this knowledge is getting aggregated by this aggregation server. And once you aggregate this knowledge across multiple dreams, so what I was showing, so imagine you have this kind of image on the right, and then you aggregate across multiple agents. And by aggregate, it just means in this context, average. So we take these images, we average them in this numerical space. And what you then get to see is averaged image at each client, which they use to train their own model. So essentially what we have done is taken this knowledge from each client's data set, combine them together, and then train a new model or train the previous model on this combined data set, and then repeat the process again and again. So you extract the knowledge from the model, combine it, train it, then extract the knowledge from this new model, combine it, train it, and keep repeating it. And what ends up happening from this process is you see this noisy image on the left. And through this multiple collaborative aggregation process, over time, it starts forming some more structured kind of image, which we see here. And then we do this training again and again, and we end up with a model output. So now let me talk about how this primitive, which I just described, enables coordination, heterogeneity, and scalability. So let's look at the problem of coordination. So if you remember, one problem which we were trying to solve in coordination was how do we figure out who should talk to whom? And today, when we are training some of these models in a decentralized manner using things like federated learning from Google or self-split learning from our lab, we usually assume you have this single or specific type of homogeneous model, which everyone is contributing to. But now that you can identify similarity by comparing dreams across different clients, you can actually create this self-organized, personalized network where people who share similar kind of data or are interested in similar kind of tasks can just exchange information with each other. So they're not sharing raw data, they're sharing these dreams, and they're able to combine their models or combine these dreams to improve their each other's model. So that's on the coordination side. And then we have heterogeneous. So in this heterogeneous case, one of the biggest benefit of this CodeDream approach is while federated learning requires you to have same model across different clients, which is not really a practical assumption because these different clients can have, or different agents, my bad, can have different resources computationally. So now you can have this CodeDream approach where models can be entirely different, but at the same time, the dreams are of similar size because the dimensionality of the data set is going to be the same. Because if I have a biomedical image, which is, let's say, 100, 256 pixels width and height, it's going to be the same biomedical image. You can always resize it if it's not. So you can have completely different models, but still enable collaboration at this abstraction layer of dreams. And because of that, you are able to enable collaboration, which would not be possible in something like federated learning. And then we show actual results in our paper that we get very close to something which would be not possible, but still think of it as an oracle where you combine all the data sets and train the models. And then finally, CodeDreams for scalability. So here the idea is that not all users will not have, let's say, data. They might have compute available with them, And then there might be some users who do not have compute available with them, but have the data. So now this ecosystem is much more scalable than something like, again, federated or traditional distributed learning, where we couple ownership of data and compute together. So now what could happen is agents who only have data can share the dreams. And using these dreams, the agents who only have compute can train a new model entirely from scratch just based on dreams. So all they're doing is something like computation. And a typical analogy would be, in blockchain, we have this notion of proof of work, where agents are not really using data, just doing this random computation, and they get something matches of hash values, and they're able to use it. And similarly here, we are able to use this computation, and thankfully this time it's not random computation, it's actually useful. So this as a sort of proof of useful work in some ways, because they are able to train a new model without having to get access to the raw data itself. And I think that's pretty much it. So putting it all together, this CodeDream framework I described, the idea is to synthesize wisdom from raw data. And you have benefits like heterogeneous collaboration, which allows different users. They have, some of them have data, some of them have compute. Now they can collaborate at large scale. Notion of collaborative selection, and heterogeneous models also, where different agents can have their own different model architecture and still be able to collaborate. So with that, thanks for your attention and looking forward to take questions and discussion.
Thank you so much, Abhi. I know we had some questions in the chat, some of which were answered, but let's just go with Adrian.
Hi, Abby. Thank you for this, particularly since I'm mostly focused on healthcare use cases like you are in your presentation. I'm curious because our work focused on the patient-centric aspect that you mentioned as being the ultimate goal in some sense of your level 3, whether you've thought about using a digital twin in a very specific way, very narrow way, in order to demonstrate what you're talking about. Specifically, there's been a little bit of research on patients being their own normal values, not having standardized normal values for lab results. So it would seem to me that it would be a lot clearer as to how to progress in the direction you want if you started with the patient-centric and a relatively narrow problem rather than this CodeDream image analysis model, which is much squishier. What do you think about that approach?
Yeah, in the paper, I do not show images here, but in the paper, we give some of the results with biomedical imaging, because then it becomes more relevant for medical imaging in that sense. Although something which we do not have here right now, but we have been experimenting with, which is related to the notion of this digital twin, is time series. Instead of looking at a single snapshot, which is this biomedical imaging example, we have time series for a patient, and then you are training these predictive models to be able to predict next time step evolution and their physiological signals and also their EHR data. And I believe that would be, I agree, if like it's a full patient-centric approach, it has to account for this longitudinal evolution. And I'm guessing this is what probably you also meant by digital twin, or was there something else?
No, I think the digital twin example covers all 5 of your requirements in that few minutes before the end of your talk, where there has to be an incentive for the individual. You have
Yes.
to have heterogeneity. You have to have all 5 of things, yes, and a crowd user experience. And so we've run headlong into this because when you export this wealth of data from an EHR and try to look through the observations, which even for a relatively well person might be in the hundreds, and say, what the hell do I do with those? I'm interested in what's the exception or what's the next step or how do I deal with a consultation? It becomes it just becomes obvious that the first thing you have to do, and it also lends itself to the privacy issues. It simplifies because you mentioned, for instance, synthetic patients as a way of avoiding some of the privacy issues or differential privacy models. It's much easier to think about what you're trying to do in the patient-centered way if you also narrow it to a digital twin for observations, not images, not diagnoses, not medications. And then you add those in as the model becomes more sophisticated over time.
Yeah, that's a very interesting perspective. Yes, I agree.
Thank you.
Other questions? I think, Jose, you had a question about heterogeneity.
Yeah, I think it got partially. I feel like I wanted a bit more detail on what you meant exactly by Abhi, but that got partially answered. I think my question revolves more around why and when exactly we define heterogeneity to be a positive thing, because there are many cases when homogeneity is when it's the opposite. Homogeneity is good, right? So, for example, when it comes to measuring units, or I don't know, laws to arbitrate between actors or things like that.
Yeah, this is, and I'm not gonna disclaimer. I feel this is something I've changed my opinion multiple times. So definitely curious to hear from others also what people think generally about this problem, because so in some sense we see heterogeneity actually helping the system overall, because different agents have different capabilities. So together as an emergent phenomena, you have a lot more capabilities. So one example in favor of heterogeneity is that previously in machine learning, let's say if we go, I guess 7-8 years ago, people would train on a single task and you would have a model which is really good on that single task. And eventually with pre-training and this whole foundation model paradigm, people came to realize that if you let the model learn all possible different tasks by combining different tasks under a single umbrella, then you have these emergent capabilities where the model can do what is known as zero-shot learning, which just means that it can do things which it was not even trained for. So in this context, heterogeneity is helping to achieve some diverse capabilities that were not even explicitly part of the input. Now, another approach where heterogeneity is actually not a good idea is, we actually found this was talking about incentives, right? So we are working on this thing called data markets, where we have two notions, diversity and relevance. And sometimes if you use too diverse data sets, then actually it starts harming the model performance, just because it is running into conflicting, let's say, information for different agents. The way we have been approaching this problem is, okay, heterogeneity is important to enable collaboration. At the same time, coordination is also important in the sense that there is some degree of relevance you want within that, let's say, sphere of heterogeneity. So if it gets too irrelevant heterogeneity, then it becomes difficult to apply. And quickly to answer your question on what are the kind of things we are talking heterogeneity about. So one is in heterogeneity of data. So different agents can have different kind of data sets, and you still want to enable collaboration between them. And then there is this notion of heterogeneity of computation or models. So you can have, let's say I have an Android phone, you have an iPhone, and we have different computation capabilities, but we still want to be able to, let's say, analyze our health data sets and ideally run the best model on device. But those best models might be different just because we have different compute capacities.
Awesome. Thanks.
Great. I think we had two more questions, Jazir and Alan. So why don't we take Jazir's and then we'll move to Alan's.
Hey, awesome presentation. There's a discussion happening. It would be great if you could opine. Alan actually asked something like, or said that privacy depends on the unexplainability of the AI output, which I agreed to, but then Micah has any thoughts?
Yeah, I'm reading the conversation right now. Okay. Also might help to define privacy in this specific context. So let's say I'm going to use a definition which is people use traditionally in differential privacy, which is the notion of plausible deniability. And I'm not saying this is the correct definition, it's just one of the definitions which is commonly used. So plausible deniability is saying, looking at the outcomes, any single individual cannot be attributed to these outcomes. It's more like a collective phenomena. It is indeed connected to a certain degree with explainability, because if your model is able to explain that, hey, I took this decision because this data point was present, then you are missing plausible deniability, right? Because you're able to tell. Let's take a very specific example. So if you're doing an epidemiological study and saying, does smoking cause cancer? And if your model is able to tell smoking does cause cancer because Sally smokes cancer cigarettes 2 times a day and she got cancer, then clearly privacy is gone. So in this notion of privacy, we do want to protect individuals, and hence the notion of attribution should not be entirely possible to a certain degree. But I'm curious if there's an other perspective there.
It sounds like you're talking about anonymity of individual patients. And I think that Micah's point is about the like homogeneity or the convergence, let's say, of information as it like becomes combined into some like average. I guess I think you want a causal explanation of why things are occurring without attributing anything to a particular individual. That's the domain space here. I have a take on this, but it's not necessarily specific to the healthcare problem. And so I think it sounds like defining our terms and like thinking about this more properly would be a better way to address like the constraint. But just seeing 2 different answers, my intuition is aligned with Alan's intuition, whereas Mike's is completely different. That spoke to me, but I think we may not be able to address this point of confusion without defining the problem space more. That's my intuition on what's happening here.
Yeah, I totally agree. In fact, even like in some of the papers, I've used different definitions. So in some cases, you might actually not care about, and just to give an example, there are situations where you don't care about anonymity, and what you care is that specific portions of your data sets is not revealed. For example, your specific health condition, which an insurance company might be able to exploit, but you still want to reveal some other aspects. So this is something sometimes known as reconstruction privacy, that you're not able to reconstruct everything about individual, but you're still able to answer specific questions. So I totally agree. I think, so if you look at the paper, we define, okay, this is what we are aiming for privacy, and this is how people have looked at this problem in this context. But I totally agree that it's contextual.
Okay. Alan.
Yeah, so my comment was more, if I share my dream with you and you can explain my AI model, you can infer at least some, if not many, of the inputs to the model. And if AI is not explainable, you can't. So if we solve the explainability problem, you'll need some other mechanism to preserve that privacy, such as mixing before revealing or something. And that was the point of the question.
But in explainability, you do not have to attribute to individual data points. So I suppose a question would boil down to what kind of explainability we are referring to. Sometimes the explainability people talk about is, I give an image to a model and then tell, can you explain your predictions for this given image?
Yeah.
Is that the kind of explainability you're referring to?
Yes, and if the explanation is I smoke 3 packs a day, I might not want that revealed. But if the model can't be interpreted that way, you're safe. But if we do solve the problem in the future, then sharing my dream today may reveal something next year that I didn't want revealed.
Yes. So I think, and that's why the field of privacy usually requires formal and theoretical guarantees. So what we typically do, although not in this specific paper we have done that, but in other papers we have done, is we will build these privacy mechanisms which have formal guarantees. that no matter what happens in the future, you cannot reconstruct or recover private information, basically. And these privacy proofs are typically based on some assumptions about the system always, but these assumptions are typically have been like well validated over last 2 decades of research. And unlike cryptography, where we assume computational hardness, which we sometimes fear that quantum computers can break, statistical techniques actually are foolproof against an attacker with infinite computation, just because they are removing a lot of information. Having said that, it does come at the cost of utility as well. If we were to increase this completeness of privacy guarantees in, let's say, CodeDream, for example, then the utility would take a hit. And there's always a trade-off. So again, something we show in the paper, like how much reconstruction you can do with worst-case adversary, and gave some results for that. And generally, I would say one thing where we are able to benefit more from privacy is because of this notion of aggregation of dreams of multiple nodes. So going back to the smoking example, although it's operating at the scale of images here, is that if we combine results from, let's say, millions of smokers, and now we have a result that smoking causes cancer by, let's say, X times in some ways. Because we have combined it from across millions of individuals, identifying any single individual becomes infeasible. And this aggregation process is what we are getting some benefits of privacy, essentially.
Yeah, absolutely. But the question is, I have shared my dream with somebody, and before it's combined, it could be analyzed.
No, so it...
My real concern is that there's a difference in the database privacy models. We know things about the knowledge data representation that we might not know. So we might be violating some of the assumptions that go into differential privacy. That was the main concern. And
yeah, no, the argument for differential privacy concerns are correct. One thing I would say, so the knowledge is getting aggregated, and this dreams before aggregation can be also secured by something known as secure averaging, which is at this point reasonably scalable. So the idea is you're using some of these cryptographic primitives to aggregate, and only aggregated answer is revealed in plain text.
And that doesn't affect the quality of the results.
No, because encryption schemes are totally lossless. But your point about the DP differential privacy assumptions are correct, because if different individual points are indeed correlated, for example, that's one assumption which differential privacy makes, that they are not correlated. But in real world, if I'm contributing my data to this, let's say, smoking study, it's very likely people around me are also contributing that data. So there could be leakage happening through other people about me.
All right, then. I think that might be it for today. Thank you so much, Abhi, for coming. Thank you, everyone, for coming. I think that this is actually the last official meeting of this year. So I hope everyone has a really happy holiday, and we'll see you in the new year.